Welcome. In this video I'm going to be demonstrating the dynamic post-processing capability of our Flexdyn segment. So in order to do that, I will start by clicking on the session manager, bringing up program. We'll be doing the structural analysis and hit continue there. And for purposes of the demonstration here, we'll be looking at this circular plate here. So it's a model that's already been run. I could go re-extract mode shapes and frequencies here by hitting dynamic, but that's already been done. I do want to take a look at it though in FlexPlot just to show you what the model looks like. So this is a simple circular plate here. It is fixed on the edge, so it's clamped along the edge, and it is 18 inches across, so fairly large, and 1/10 of an inch thick, and it is a steel plate. So we've already extracted the mode shapes. We want to take a look at what those look like. We'll look at it from the side here, and we'll come down here and hit mode. And there's our first mode at 122.5 hertz, and I can animate that by hitting animate. That's what that looks like. That's just our first symmetric mode there. I'll come back in here now and hit mode number to 2, and that's what the second mode shape looks like. So that's let's go ahead and rotate the screen a little, not the screen, let's rotate the global axes, the x-axis by, let's say, 10 degrees. Get a little bit better look at what it looks like. Okay, and now then we'll go animate. So that's what that mode shape looks like, anti-symmetric mode. We'll go to the third one, another anti-symmetric mode, 90-degree shift from the previous one, and that's at 255 hertz. And then the final one is getting a little bit more complicated here, and it looks like that. So we'll be analyzing this plate here in those 4 modes. Okay, so we will hit stop here, exit that, and we'll go into Flexdyn. So we'll click on Flexdyn. Okay, so it pulls up the information on the plate there, and we're going to be doing a steady state analysis to begin with, a harmonic type of analysis. We'll click OK there. And then over here there's a couple of things we need to fill out here. The little check boxes will tell you if it's done or not. So that's analysis type, and we've selected the steady state. We'll come down here to frequency limits, and we're going to be plotting, looking at from 10 to 1,000 hertz. We'll do that. And then forcing function type, F type. So to begin with, we'll be doing just a nodal force, and the center of the plate is node number 1. So we'll be applying a sinusoidally varying nodal force at node 1, and we're going to want it in the z direction. That's the perpendicular to the plane of the plate there, and we'll have it at a amplitude of, let's say, 10 pounds. So we'll hit enter there. It gives us the information there, and then we could have multiple nodal forces. We could change it to a nodal moment on a different node and so on. So we could do a lot of different things combined. We'll hit OK there. And now we want to determine the response type. So what do we want to look at? So we can look at displacement, velocity, acceleration, or stress in an element. And to begin with, we'll just look at the displacement at the point of application of the load, which is node 1, and we're going to look at the z translation there. So we'll click OK there. And now we just hit calculate and let it go calculate. So these are the results. So this is a 10-pound steady state nodal force on node 1 in z translation, and it's got an amplitude of 10. So if I sweep 10-pound force across this frequency range here, this is what the response of the plate will look like. And you can see that the z translation of node 1 is a maximum of just about a tenth of an inch here, 0.09 inches. So now if we wanted to determine where is the largest displacement on the plate under that loading condition, we could come over here and just hit scan, and it will look around and say, okay, so I am right at the maximum displacement, which isn't a surprise. It's right underneath where the load is being applied in the center of the plate. So a large steel plate, tenth of an inch thick, 10-pound oscillating force in the middle, you get about a tenth of an inch displacement. So now let's go back and look at response type, and we'll do stress response here, and we'll hit OK. And I'm not sure what element I want to look at yet, so I'll just go with element 1 there and hit OK. And this is a plate surface, so I can look at either the top surface or the bottom surface. So in this particular problem, it doesn't make a lot of difference which one you look at. We'll just leave it at the top. We'll hit OK there. And now then, what stress do I want to look at? Okay, well, I can look at maximum principal, maximum shear, von Mises, which is typically going to be the highest one, or some local element stresses there. So I'll click on von Mises and hit OK. And now where in the element do I want to look at it? Well, I can look at it in the center or the IJK. This is a triangle, so the IJK nodes. I'll just leave it at the center there and hit OK. Okay, and it just gives us a summary over here of what we just selected for this case. So I'm going to hit calculate there, and it does the analysis, gives you the information about what we're looking at here, and we have about 9,000 psi of stress at that extreme fiber there. So now here though, I can hit scan again, and it'll look for the highest stress, the highest von Mises stress in all the elements under the given condition. So we'll hit scan there. It comes back and tells us that element 305, it's got about 12,700 psi of stress, and that's the highest that it found. So we'll come back here and just check on that, and we'll do a stress load again, and here we'll put 350 there, that element number, out of range. Okay, I'm sorry, it's 305. 305. We'll do that. We'll leave it there. We'll do the von Mises, the center, and we'll hit calculate here. And there it is, 12,700 psi in that element. So the damping has already been preset, which you can change, but for all the modes, we have 4 modes here, and the damping is set at 2.5% of critical. So we'll just leave that alone there. And you can see here we've got 4 modes. These are the frequencies from 122 hertz up to 415 hertz. Okay, so let's go back now, and we'll try a different analysis type. I guess first of all, before we do that, we'll keep with steady. We'll do the same frequency limits. The forcing function, though, now let's go with a base motion. So this will be a base of that fixed edge around there. That will be the base motion that will be right there. And we'll do a constant amplitude translation there, and we'll put down 10 G's that I want to do it in. So I can do some other things, rotation, constant amplitude rotational acceleration, or the double displacement amplitude versus frequency, which you see frequently. And we'll leave it at the Z translation, and we'll go OK there. And the response type, what do I want to do? Let's go back and look at displacement again at node 1. We'll hit OK there and hit calculate. And there that is. So again, we've got about 0.2 of an inch displacement there at that first natural frequency, which was 122 hertz there. So that's that right there. Okay, now if we change the analysis type to random, and so this is a random vibration analysis, we'll do the same frequency limits, the forcing function now on this though is a PSD, so you want to input the g squared per hertz for the PSD across the frequency range there. We're going to do the standard 4-point and Z translation, and I'm just going to leave it with the pre-selected ones here. So frequency, the first one, F1, is 20 hertz, 100 hertz, 1000 hertz, and then 2000 hertz. And you can see the values here. So we'll hit OK there, and it gives you a picture, draws a little graph of what that PSD looks like. And then it will also integrate it and tell you that this is a 5.3 GRMS PSD here that we're subjecting the plate to. So we'll do displacement here again for node 1, hit OK, and go calculate. And you can see that displacement is very small, and this is the relative displacement in inches squared per hertz here. So you can see what that looks like, and so on. So that's a random analysis. You could do the same type of thing, look at velocity, acceleration, stresses, and so on. So a little bit more interesting, we'll go back and do a transient analysis here. Click on that, and now we don't have a frequency limits here. We do have the forcing function type though, and what do I want to do here? And I'm going to come over here and pick one of these predetermined shock forms here, and we'll do the square wave here. And then the duration, we'll put down 10 milliseconds, and the peak force, let's put down a 10 pounds. So we're subjecting it, node 1 there in the center, to a shock there, a square wave shock, 10 milliseconds of duration, peak force of 10. I'll look at it over the 50 millisecond time range. I could, let's change that to 100. And then the time step will be a tenth of a millisecond. So we'll choose OK there, and now the response type, I'm going to do the same thing. I'll look at displacement at node 1. Okay, we will go calculate that. And here's the time history of the response of that plate there. So a lot of ringing. It's 2.5% damped, so you could calculate what that is from the decay here. But you can see that the maximum is going to be about 1 mil, I believe, or 9 mils, I'm sorry, is the maximum displacement there with that shock. So, and you can see the time duration, and so on. So you could look at displacement. We could go back and look at velocity if we wanted to, and you would calculate on that. And that's what the velocity looks like, so on. And you could also go calculate what the frequency is, and you could you'll note that it'll turn out to be the 122 hertz there. So okay, we can swap back to the text screen here and look and see what all we've done here in this session. We've done 8 cases here. There's our transient is the 8th case. We did 2 transients, that's 9, and so on. So you can swap back and forth between the graphic and the text there. Okay, so that is a pretty good summary of what you can do from a dynamic analysis standpoint with Flexdyn. So we'll hit stop here and exit, and we will exit out of the session manager. So thank you very much.